Assalamualaikum warahmatullahi wabarakatuh. Sorry, ada interruption sikit tadi. Okay, we may begin insyaAllah. My voice is better now.
You will start now, Prof. Norita.
Oh, I can start. I can start straight away.
Okay.
Okay, can. Okay, thank you, Prof.
Yeah,
Okay. Assalamualaikum warahmatullahi wabarakatuh, and good morning to Prof and any other lecturers if they are around with us. Sorry, and also to all my dear students. Bismillahirrahmanirrahim. So today we are going to proceed with our second lecture, but before that I'm going to do a recap, a brief recap, and then I will give you a short quiz. Okay, I will share the link with you. I will give you a short quiz, and then we can go to the second part of the session. 1 minute, yeah, I'll share my slides now. I hope everybody is in good health. 1 minute. Advanced sharing. Where is the? Okay. Okay, that's. Can you see my slide, class?
Yeah, on process. Okay.
Okay, thank you. Good. Okay. Okay, I will do a bit of recap, yeah. Sorry. Okay, last week we have looked into OPM, and we have also looked into the capability of our OPM when it comes to voltage gain. Okay, it can be around 1,000 or around 10K or maybe even more, as long it doesn't goes out of the positive saturation and the negative saturation. And you know, why is it that this particular 741, yeah, it is called operational? Okay, I mean, it's called OPM, operational amplifier, because we know amplifier is something that we can use to amplify signals. But this 741 is a bit unique, that we put an adjective in front of it with the word operational, because it can actually operates, or it can actually perform several mathematical operations. Yeah, and last week we have seen how our OPM can be functioned as a summing amplifier, as a differentiator, yeah, as a subtractor. Okay, it can. This week we are going to do. We are going to look at how it can do differentiation and integration, and we are also going to see how our OPM can actually perform filtering. Okay, low pass filter, high pass filter, and band pass filter. So this is again recap. Okay, our OPM, there are two things that we look into last week, which is the ideal. Ideal ni maknanya theoretical punya value, ya. The ideal characteristic of an OPM. But if we go to the labs, practically what will be the value? Okay, so a good OPM, okay, if you want to do some troubleshooting, etc., a good OPM, one thing we have to ensure that it can actually amplify, which is it has a very high voltage gain, maybe in order of 10 to the power 6, and the input resistance is high as well, and whereas the output resistance is low or small, which is to ensure that all the signals being amplified is sent to the output. That is an indicator, the three indicators of a good OPM. Ideally, when we say it is a good OPM, okay, meaning when we say it's high voltage gain, the OPM gain is infinity. That is ideal, or infinity means a very high value. Okay, and the output resistance, when we say a very high, ideally it means the input impedance towards infinity. And the output resistance, when we say it is low, meaning it is approaching zero. this is just a table that actually mention all those three characteristics and also the supply voltage. Of course, you know that op-amp, it needs to have a supply voltage for it to operate, yeah, and the typical values and the ideal values in terms of infographic. Okay, this is an inverting amplifier. How do we know that it is an inverting amplifier? Because the voltage source is connected to the negative supply. Yeah, it has two inputs, which is inverting and non-inverting. So this one is inverting. Why? Because the voltage source is connected to the inverting inputs. Okay, this is when we use op-amp as a summing amplifier. Yeah, we input all the sources, okay, to the inverting input, and we actually look into last week what does this negative means, meaning it is out of phase. Not to say that the value is less than 0 or what, no, it's not that kind of indicator of negative, but it is to tell that the input signal and the output signal is out of phase. Okay. Okay, this is a non-inverting. How do we know? Because the input impedance, the input voltage is connected to the positive terminal. This is the equation for inverting input. This is the equation for a non-inverting input, and this is another way of drawing the non-inverting amplifier. Okay. Okay, a little bit more before we go for our pop quiz. Okay, a voltage follower. Okay, a circuit is something that how we fed the input signals to the output. Yeah. Okay, that is actually a voltage follower, and this is the differential amplifier, which means differential di sini meaning it conducts the subtraction, the difference between two voltage source, which is subtraction. Okay, so both inputs on inverting and non-inverting are fed with voltage source. In this example, it is VA and VB. Okay, from the derivation, okay, when we assume all the resistors are equal, then we will have that the output voltage will be the difference between VB minus VA, okay, times by the voltage gain, which is the feedback resistor RB over RA. And how do we get the point P here? Is from the voltage divider rule. And what is the point N here? We assume it is virtual ground. Virtual means, which means when we do the computation, when we derive the formula, we assume it is connected to ground. Okay. Okay. This is not quiz yet, but I just want to refresh with you. Take out a piece of paper or whatever that you have. Try to do this question. Okay. Sila. Class, if you have any question, please feel free to ask me at the chat box. I want to look at the chat box. I will give you the solution after that, but I just want you to refresh back. I want you to check yourself that you really understand or you understood whatever the concepts and the notes or the content that we have learned that we have learned last week. There's one. Jika ada pertanyaan bias disampaikan via chat, question can write on chat. Yes, can Prof? You are required to determine the value of V out. And the question has actually mentioned that you can assume that it is virtual ground, yeah, for N, okay, and VP is equal to Vn. And the current IP and IN, okay, there's no current towards the inputs, the terminal of the op-amp, input terminals, and we can assume everything flow here this way, yeah. This is quite straightforward actually. When looking into it, it is actually inverting input. Yeah, Muhammad Iqbal, your hands are up. Yeah, you may ask.
The power PO is -2.
-2, yeah, correct. Wait 1 minute. Very good. Yeah, the solution is there. So I hope everyone also gets the same answer like Iqbal. Thank you, Iqbal. The answer is yes, -2 volt. So how do you get that? Based on the assumption that they allow as given above, okay. We compute I, okay. So V out over RF is given as 200K plus VG divided by RS, our RS is 100K, is equal to 0. Then we will have this. So we have given VG is 1 volt. So -2 times 1 volt. So we have our output impedance as -2 volt. The negative is indicate it is actually out of phase with the as compared to the input voltage, and you can also straight away use RF over RS. Okay, V out is RF over RS times by VG, because they allow us to actually assume virtual ground. Okay, so this is actually, we know it is inverting input, and the formula for inverting input is minus RF over RS here. This is actually the configuration. Yeah. Okay, good. Second question. So the question says, in the circuit below, find the output voltage for negative feedback operation. So when it says that negative feedback operation, meaning the op-amp is function as the inverting input. So how do we know that it is operating as an inverting input? Is to see which terminal X or Y is being fed with the source. So in this case, the Y is being fed with the input source, meaning Y is the inverting input and X is the non-inverting input. Okay, and from there you can actually compute now the rest of the. Yeah, this is the solution. It's a bit long. So this is the original question. So we say that Vx is equal to Vy because of the virtual ground assumption, and you apply a voltage divider rule at Vx, you will get Vx is equal to 1K over the total voltage, okay, times by V out. And we know that Vx is equal to Vy, yeah, is equal to V out over 2, okay. And you apply KCL, Kirchhoff current law, I, Y, and here, okay, and you have this, okay. You have V out is equal to minus 4 volt. You replace Vy as V out over 2, and you have V out is minus 4 volt. It's a bit long. Okay, we'll go to the next question, question 3. The circuit is similar. In the circuit below, find the terminals of X and Y for the circuit to be in negative feedback. Okay. Okay, and we have already seen just now that for it to be in negative terminal, yeah, Y is the negative terminal, like I explained how, because the source voltage is connected to Y, so Y is the negative terminal and X is the positive terminal. Okay, the fourth question, compute the value of Ix. Okay, this one you try to do. Not to worry, I'll pass the slides, today's slides as well to your professor for you to have a copy of it. Yeah, so if you want to look into the solution, detail everything, you can take a look later on. Okay, try this one, and after we will go for our pop quiz for 20 minutes. Okay, let's look at the solution. Okay, so how do we compute Ix? First, we compute I1 here. Yeah, I1 from the source. Okay, and we assume that this is virtual ground. Okay, so Vn and Vp, there's no voltage drop there. So I1 will go through here, okay, and we have that 4 minus Vn divided by 6K, and we know Vn is visual ground, so it's 0. So we will have I1 as 2.3 milliampere. Okay, so once we know what is I1, okay, we can compute Ix, okay, because we want to know what's the voltage drop here. So Vx minus 0, which is Vn here, divided by 3K, the resistor, yeah, we have minus 2.3K milliamp. 2 divided by 3K milliamp. Sorry, I'm so sorry. 2 divided by 3K, which is the resistor, minus 2 divided by 3K, because Vz, we know it is minus 2 divided by 3, okay, K milliamp. And then from there, we can compute that Ix is 0.67 milliamp. Sorry, okay? So I think I have refreshed you and recap what we have learned last week, so that you can actually recall back and you can answer well in your pop quiz. Okay, I'll share the link with you now. 1 minute. That's the link. I'll share in the chat box. Yeah, I stopped sharing for a while. It's okay. So I just put it here. Chat. Okay. You just click, and after that you can straight away answer. Okay, all the best. I put my timer. Anyone, if you cannot access, please let me know. But I think I opened it straight away for everyone. One student submitted. You still have time. Okay, 16 students submitted. I am monitoring the response here. Twenty submitted. So you have another 2.5 minutes, yeah? And after that, I will stop receive responses. Another 2.5 minutes. 40 of you have submitted. Okay, you have under 40 seconds. Come on, class, finish it. There are 74 of you online today. I have only received 50, another 24 to go. I will pass the score to your professor after later on today for him to have a copy and see your performance. Okay, time's up. Submit. I will stop receive response. Yeah. Where is the? Okay, I will stop receive response. Whatever you have, just submit, and I think 20 minutes is more than enough. What happened? I only received 54. Why is the rest not sending? You don't want to try your, you don't want to test your understanding, is it? Only 54 responses. 55. You need to submit now. I'm going to close the button of accepting responses. Please submit now, or else I will not capture your results. Okay, I'll stop now. Okay, I stop accepting responses. I am receiving only 55. I'll just show you the screen, yeah, so that you know how do I monitor your, you can see that. Look, I have 57 now. This is the button. There are 74 of you online, exclude myself, exclude your professor. So 72 of you. I only received 57. I don't know what happened to another 15. Once I off this button, your results will not be captured in my sheet. Okay, this is the responses that I have received. Okay, for all the 57. Okay, I'll stop now. Yeah, I think it's more than enough. Thank you. Okay, so no longer accepting responses. So you know what's your score, because I actually set as such that once you finish answering, you know what's your score. Okay, so any of you that receive 8 and above, because we have 15 questions and it's multiple choice, or any of you that receive 8 and above, meaning at least you have understand what we have learned all this while, yeah, about operational amplifier. So for those with 7, there are 4 of you, 6, 1 of you, with score of 4-1 and score of 2-1. I think you need to put a little extra effort. It's actually indicating that you need more time to really understand the basic concept and function of operational amplifier, because the questions that we actually put up is to test the fundamental understanding. Yeah, because if we don't understand the fundamental understanding, then we could not proceed with answering the questions and what not to mention design, etc. Okay, it's not too late. It's never late when it comes to learning. Okay, you still have time for you to improve. Yeah, inshallah. Okay, so the detail of your score is here. Okay, I'll pass to your professor later. Okay, that's it for today. When for quiz, we come back to our notes. Okay, I'll share the screen for notes now. Okay, last week I have mentioned to you something about slew rate. So what is actually slew rate? Okay, so when we say that a slew rate occurs in an op-amp, what is actually happen? Okay, the rate of change at the output voltage versus the input voltages, causes some delay. But the delay is actually could not be captured by our eyes because it's very fast in terms of microsecond or millisecond. So it's normally worst case is millisecond. Okay, so when we say the slew rate of what is the slew rate of an op-amp is actually the rate of change at the output voltage caused by a step change at the input stage. Okay, and normally the voltage change when it comes to op-amp is typically around volts per microsecond or volts per millisecond. So ideally, okay, if this is the input voltage, okay, so the output voltage will change immediately, meaning from 0 and then it goes up high and then down. Okay, at this point and this point. At this point and this point. However, practically, that doesn't really occur, meaning there is a delay for the output voltage, okay, to change from the low edge to up to the highest edge. It is not a perfect straight like the green one, but it is something slanting like this. That is practically what happened, and that is known as the slew rate of an op-amp. Okay, so an op-amp device may have a slew rate of maybe 10 volt per microsecond, which is acceptable. This means when there is a large step change at the input voltage, okay, the electronics device, okay, will only be able to provide an output 10 volt change in 1 microsecond. They are the delay 1 microsecond, but 1 microsecond is very fast. Even 1 second is fast. 1 second, pop, 1 second. But 1 microsecond is actually something that our eyes could not capture, but it occurs. And when it comes to electronics, it matters. Okay, so we don't want this slew rate to exceed a certain value. So when you go for your design, you need to actually look into the slew rate of the op-amp, the allowable or the acceptable slew rate when it comes to the design. Okay, now we are going to this is just explanation. You can read it later on, but I have actually explained to you what this slew rate is all about. So we're going to now, we have seen actually op-amp last week. Now we are going to see op-amp as filters, and the 3 category of filters that we're going to look today is low pass filter. What is low pass filter? High pass filter and band pass filter. Okay, a low pass filter, meaning when we say low pass filter, what does it do? Okay, meaning it allows low pass filter. It allows low frequencies to go, and it does not allow higher frequencies to get through. That is the meaning of low pass filter. It allows low frequency. So low pass filter is a filter that allows lower frequencies to get through, or passes the lowest frequency and rejects higher frequency. So we need to know in every filter what is the cut-off. That's the term we use, cut-off value for every filter. Every filter needs to have its cut-off, meaning at the cut-off it will allow, after the cut-off it will not allow. Okay, so low pass filter, where actually we use low pass filter. So some example of usage of low pass filter is in analog to digital conversion circuit block, that it actually limits the high frequencies to enter and to prevent aliasing. This one you will look into when you go for your digital system. Okay, also low pass filter is used in DAC, okay, digital to analog conversion, to remove aliases at high frequency, and also used to prevent harmonics. Okay, when it comes to signals that is being amplified or radiated, and also it is used normally after radio frequency mixer, which is actually the purpose is to remove any unwanted high frequencies that is being generated at that particular mixer. So that is the example of low pass filter. So these are one example of the circuit. Yeah. So low pass filter normally being utilized in electronic circuit design, where low frequencies are actually required, but higher frequency is not needed. So we actually does not allow it, or we reject it, okay, at the circuit. So this is one example of the plots for low pass filter. This is the point I mentioned to you, the cut-off frequency. And we need to actually be able, or we need to know what is the cut-off frequency, because we want to know that it will allow until what frequency. Okay, so that the cut-off frequency is very important, and we need to be able to compute it. So for low pass filter, meaning it will allow any values of frequency from 0 right up to before the cut-off frequency. Yeah. So this is another example of low pass filter when if we use it using op-amp, be it non-inverting configuration or inverting configuration mode. Yeah, anything? For Salim, anything? Okay. Okay, thank you.
I'm sorry, Miss.
It's
Kepencet.
okay, it's okay, no worries. I thought you want to ask question. No worries. Okay. Thank you. Okay, so low pass filter, how actually the circuit comprised of? Actually, it comprised of a combination of resistor and capacitor as such, which means resistor and capacitor in parallel this way, okay, at the feedback loop. Yeah. That actually controls the filter effect. Yeah. So the equation is simple. I think all of us has seen this impedance equation, which is 1/2 pi FC, and XC is the capacitive reactance. Okay. And pi, I think everybody knows, we normally assume 3.142. Frequency is at what frequency that is going to function, and C is the value capacitor in farads. Okay. This is actually another way of also a low pass filter, but we use two pole, meaning we have one capacitor and resistor combination here and another one here. Okay, so if this is the case, we will assume that R1 normally the value is equal to R2 and C1 is 2 times C2, and this is how the frequency that we are going to compute to get the cut-off frequency. Okay, let's see the first question. Take out your piece of paper. Okay, with what I have explained to you, okay, using the single pole or the double pole, okay. Try, this is actually designing the filter. I will give you the solution later on, but I just want you to try and see with these 3 slides that I've explained, what actually that you have understand so far when it comes to low pass filter. Okay, so what the question asks us to do is actually for us to design the filter, and it tells us that, okay, we are going to use non-inverting active low pass filter. Non-inverting meaning the configuration will be something like this. Okay, and the cut-off frequency is at 160 Hertz, which means the cut-off here is at 160. It can only function between 0 to 160 Hertz. Anything above 160, your low pass filter will reject. Okay, and input impedance is 15 kilo ohm. 15 kilo ohm means XC. Here, this one, XC. XC is 15K. Okay, so what you need to do is assume that at low frequency, this circuit has a voltage gain of 10. Okay, so design the filter. When it says design the filter, what the question asks you to do is, we need to know what is the value of resistors and the value of capacitor in this circuit. No, sorry. In this circuit. This circuit. we are doing this circuit because it has actually informed us it's a non-inverting amplifier. Okay, try first before the solution is there, but you try first. I just want to go and get some water, yeah. Did you manage to start? How do we compute R1 and R2? I'm going to guide you here with the solution. Okay. This is the circuit that we're going to design. Okay. And we are given the cutoff frequency at 160 Hertz. And XC is 15K, voltage gain is 10, remember? Okay, so we know that this is not inverting, yeah? So voltage gain 10 will be 1 plus R2 over R1. Yeah, and we let R1 be 1.2K, so R2 will be 9R1, so it will be around 10 power of 8K. But practically, there is no resistor value as 10.8. The nearest is 11K. Because when you want to go for design, you have to relate with the actual practical values of resistors that are available in the market. Okay, 10.8 kilo ohm tak ada, 11K ada, 1.2 ada, 1.2 kilo ohm ada. If you go to your laboratory, you tengok nanti dekat laci-laci tu kan ada all the resistors ke kan. And then you know what is the practical value. 1K, yes, we have, yeah, 1.2, 1.5, 1.8, yeah, but we don't have 10.8, okay, sebagai satu. But we can have, of course, series, but that is not the design that we want. So normally kalau kita design, if we calculate it as 10.8, you take to the nearest standard values available. So the nearest standard value yang ada adalah 11K. So we know that we are given XC is 15K. So from the and also we are given that the cutoff is at 160 Hertz. So we straight away can compute what is C. So we have C around 0.068 microfarad. Okay, that's how the design of our circuit. Yeah. So the cutoff is here. That's how the plots look like. Okay, any questions on the solution that you maybe want to know more? Please ask. You will get these slides later. Okay, good. Okay, we proceed to again. We are still under low pass filter. Okay, we are given this circuit again. Now it is inverting, and we know that low pass filter normally will allow low frequency to go through. However, higher frequency will be rejected. Okay, so we need to actually determine the highest frequency to pass through the filter. For this particular example, you are given the frequency value, the cutoff value, you are given the input impedance, etc. And you need to compute what is the value of R and C for you to design such filter. For this particular example, you are given the resistor and capacitor value, and we need to actually compute what is the frequency. Yeah. So determine the highest frequency to pass through the filter. This is the cutoff frequency F. So we again use this equation. Xc is 1/2 pi Fc. We have C, we don't have F, okay? And we need to compute what is Xc. Yeah. So for example, if F to be 2 kilohertz, we choose the capacitor and next match the resistor network. Okay, so for this particular example, let's say F is at 2 kilohertz, F here. Okay, and we have what is R and C. Here is given as 100 nanofarad. So the value of R is approximately 800 ohms. Okay, we compute and we have set 795.77. We straight away go to the nearest value, which is 800 ohms. And the filter can be designed if R2 over R1 so that it is unity gain 1. So again, we assume that R1 is equal to R2. That's how the actually the how actually we set the frequency to be, okay, for this kind of filter. And this is how the plots look like, okay, for that particular filter at 2 kilohertz. Okay, 2 kilohertz is somewhere here. Yeah. Okay, there's one question. I'm curious about that band pass. Can we tune that band pass shape to more sharper? If so, what is the main variable we must consider? Okay. Bagus. We only now we are going to the band pass. Just now it's low pass filter, yeah. This is low pass filter. Okay. Only now we are going to band pass filter, and you will see how you can actually tune for it to have that the lower end and the upper end, for it to be in between there. Okay. So this is a band pass filter. Band pass filter is actually a low pass filter cascade with a high pass filter. Okay. By right, I should teach you high pass filter first. So I'm going to high pass filter first, then we go to band pass filter. Okay, this is high pass filter. Okay, so if low pass filter allows low frequency to go through and rejects high frequency, high pass filter will do the opposite, the other way around. It allows higher frequency to go through and rejects lower frequencies. Okay, so this is the configuration of a non-inverting high pass, where you can see the resistor and the capacitor is in series. Just now, for low pass filter, you saw it in parallel as such, yeah. But this one is in series, yeah. So, where do we actually utilize high pass filter? Normally, it is actually to reduce hum or noises, okay? Because high pass filter, normally they are able to provide a high level of performance from small electronic components, and the cut-off frequency or the breakpoint of the filter. We are only using one formula, but it is just which filter are we talking about? Okay, all the formulas are Xc is equal to 1/2 pi Fc. But is it now we are talking about low pass filter or high pass filter? Okay, this is one example of op-amp circuit for active high pass filter. Okay, where R1 is equal to R2 and C1 is 2 times C2, and we have this. This is for 2-pole. Yeah. Okay. For this 1-pole, yeah, high pass filter, similar to low pass filter, the only difference is the capacitor at the input resistor. If for low pass filter, the capacitor is parallel with the feedback resistor. And the equation for determining the cutoff frequency is also similar. Okay, only that now the frequency below the cutoff will be rejected. Okay, so I want you to try this for high pass filter before we go to band pass filter. Try this question. A high pass filter has a pass band gain of 2, yeah, and a cutoff corner frequency of 1K, which means that is actually the cutoff frequency. Cutoff frequency here. This is high pass. It starts here, meaning anything below 1K, it rejects. Anything above 1K, it allows to go through. Okay. If the input capacitor is 10 nanofarad, compute the cutoff frequency. Okay, determine the cutoff frequency determining resistor and the gain resistor feedback network. Also plot the expected frequency response of the filter. Okay, I want you to try this, which means you need to compute the value of R1 and R2. Okay, and also what will be the cutoff frequency. Try first before I give you the solution is there. Not to worry, the solution is there. But I want you to try first. Okay, I'm going to share with you the solution. Okay, we are given that the corner frequency, the cut-off corner frequency is at 1 kilohertz, 1 kilohertz, and the capacitor value is given as 10 nanofarad. So from there, we can compute what is R, okay? We know that R is 1/2 pi FCC. So the input impedance is around 15.92 kilo ohm, okay? And we round it to 16K. And we are also given that the voltage gain is 2, and this is and the cut-off frequency. Okay, sorry. A high pass filter has a pass band gain of 2, which means the voltage gain is 2 here. Yeah. So from there we have the R2 over R1 is 1. So which means R2 is equal to R1. Okay, that's the normal design of op-amp. So if we assume both as 10 kilo ohm, okay, you will have your plots, okay, your voltage gain plots as such. Yeah, we know that voltage gain V out over V in is the feedback over all this. And if you compute one by one, you will get this kind of data or table. And that's how we actually plot the voltage gain. Sorry, the frequency response. Yeah, based on the voltage gain and the gain here. This one is not, this one we need to compute one by one. Okay, what I have given you here is actually the answer straight away. You need to plug in into the equation. Only you can plot here. Okay, so we are given that the cutoff is at 1K. So anything above 1K, it will pass through. Anything below 1K, it will reject. This is actually the application of high pass filter that is normally used in audio system, speakers, which is actually to reject noise, okay, or sometimes distortion, yeah. And sometimes this high pass filter is also known as treble boost filter because it can actually reduce the noise in speaker and amplifier. Yeah. Okay, that is high pass filter. Okay, after this we are going to band pass. Okay, why? Because now you know what a low pass filter is doing, what high pass filter is doing. Only then we go to band pass because band pass is a combination of low pass and high pass. Yeah. So this is actually a band pass filter. Okay. So if we look here, band pass, okay, from the plots of frequency first, yeah, we know that this is actually the high pass, sorry, yeah, the high pass, and this is the low pass, yeah. So the circuit will be the combination of low pass and high pass circuit. So we have a high pass and a low pass. So combination of a low pass and a high pass filter, where the R1 C1 combination forms the high pass portion, and the feedback R2 C2 perform the low pass portion. Yeah. So ratio of R2 R1 normally is similar. That actually determines the voltage gain of the amplifier. And what we need to do when we design our band pass filter and how you're going to tune it. I think one of you asked me about the tuning. What are the values actually? Okay, the highest and the lowest, the highest and the lowest frequency that your filter wants to allow to pass. So these two corner frequency that you need to compute, and you need to have a reasonable bandwidth. Janganlah cepat sangat sini lepas tu terus turun. Nanti bandwidth dia kecil sangat. It doesn't actually serve the purpose as a band pass filter. The allowable start and end should be sufficient for it to actually function as a good band pass filter. Yeah. So we need to actually compute the lower end and the higher end of those filter. So using again the same equation, Xc is equal to 1 over 2 pi Fc. Okay. So where normally we use band pass filter? Band pass filters are normally used in application like for a single band frequencies required, okay, and where we need to actually accept and reject certain amount of frequency at the lower and the upper end, okay, normally band pass filter, op-amp as band pass filter, okay, we can create using this very minimal number of components with two capacitor and 3 resistor and 1 op-amp. Okay, we can already have our band pass filter that can perform and be used in several electronics application. Okay, so from this circuit, okay, we have the R1 is Q, H is to actually for us to compute this, okay, where H is actually the gain, and this one is the 2 pi F, okay, and R2 is as such. And how do we compute the R3? This is actually the band pass filter response, and this is what I said, I mentioned earlier, the bandwidth, the allowable bandwidth should be sufficient or acceptable. Okay. Okay. We are going to see one example where we require 2 corner frequency. This is band pass, yeah. The lower part we want it to be 200 hertz, and the upper part we want it to be at 2 kilohertz. Okay. So again, using the same equation, we can compute what is the value of R or RNC. Okay. And normally, we will choose R2 and R1 first based on the gain given to us or the gain that we want to achieve. Only then we calculate the value of C1 and C2. Yeah. So for this particular equation, you can try this on your own because it's using the same equation. We can have R1 and R2 around 10 to 8 kilo ohms with C1 and C2 between 10 to C1 10 nanofarad and C2 100 nanofarad. So when you look at this kind of plots, yeah, on the scope, on the oscilloscope, okay, the things that you need to actually look into and confirm is the lower cutoff frequency, the lower cutoff in between the two cutoff frequency, the lower and the upper, the high cutoff, and beyond the high cutoff frequency. Okay. This is another example of band pass filter, but we use it, we call it as a two-pole. Huh? That gives the similar results like the earlier one. Okay, we have high pass filter op-amp. Remember this, when you have capacitor and resistor in series at the input voltage. This is high pass. This is the low pass. Okay, so the high pass followed by the low pass, and when we cascade both of these, we will have a band pass filter. Okay, this is high pass filter. Okay, okay. Somebody asked me just now. Bagus. I'm so sorry if I pronounce your name not correct. Yeah. Bagus, okay, Jayendra, yes. What is it that you wish to know more? What to tune? Does the explanation just now answer your query, Jayendra? Here?
I think it's about band pass filter. Something that I want to know more about the band pass filter is like, if you ever already tried about parametric equalizer in some like audio equipment, you know that every equalizer have a slope that you can tune to like how much frequency you want to cut, and like the first question, like I have sound above. Can we turn the bandpass step to more sharper? I think I need more explanation about that, Prof.
Okay. For you to overcome that, is it? For you
Uh,
to overcome your problem, is it?
Yes, yes,
Okay.
Prof.
Now what is the lower cutoff and the higher cutoff frequency and the total bandwidth of your bandpass? Did you actually take a look or did you compute that?
Actually, I'm not computing about that because I'm using plugin that everything is must be like plug and play. So I just
Tune it. You just try and error and tune, is it?
yes,
Ah,
yes, Prof.
I think I would like you to suggest, I would like to suggest to you if you can actually look into what is the lower and upper, and we have some idea what is actually the range of the bandwidth, because I am afraid that I'm not sure because I don't look at your circuit or your whatever yet. Maybe, you know, it needs to be a bit expand the bandwidth. Maybe. Can you try that?
Can I share my screen, Prof?
Yeah, sure. Sure. I'll stop sharing. Yeah. Sila. Ya. Nampak macam sangat small lah dia punya. Cepat sangat dia ni. Okay. Yeah, no, that is not a band pass already. Okay. I think you should go for band pass wide. Try band pass wide. Okay, if you go for this, what will happen to your sound? How do you confirm that your design fits your purpose?
Hello.
Ya, saya dengar. Saya tak dengar, you tak reply lagi.
Okay. I think I will repeat. This is a band pass that I chose from the preset that I set in my plugin.
Okay.
My question is, can we still do the same thing in analog electronic? Like I change this resolution and like this. Can we change it? Because it's already did in digital, so it must be we are not calculating something because it has been already programmed.
Yeah, I
Can
know.
we? Yes.
Can you change it to 24 dB whatever, is it?
Yes, but in analog terms.
Okay. First, I understand this is actually a software that can straight away you plug and put the values, right?
Yes.
How do you test whether it's 12 dB or 24 dB that fits your design? How do you test whether whatever that you have choose like 12 dB, then you test it to do what?
I'm using external grep like this. Wait. Insight Pro. Now, this is the plugin that we can
Yeah,
see
understand.
how much frequency we have already cut from the bandpass.
Okay.
And if I have a testing like giving a sound this,
Okay.
wait, there's another problem from the software.
So I can't hear the sound. Huh? Does it supposed to have any sound?
Yes, it already has a sound, but I think the sound is not.
Yeah, yeah. Maybe only you can.
Yes. Can we do this in analog electronic too, Prof?
I guess yes, we can. Why is it?
If so, what kind of electronic component we need to turn like this? It must be something a variable we concerned to, because it must be like this.
Doesn't it have an op-amp inside here in the library? No.
No, Prof.
Oh, I understand now. You want to use what component to design this, is it?
Yes.
Yeah, I understand now. Active filters will be op-amp. How do we? Normally it's op-amp, or else you have to use. Let me see. Normally it's op-amp. 1 minute. Can you just take a look at? Have you seen Butterworth filter before this? Butterworth filter.
I think I never seen filter like that, Prof.
I am just suggesting to you, maybe after this you search for Butterworth filter and look at the design, because op-amp is one of the active filters, which means we use this. I put it in the chat box, the name. Then you look, because if Butterworth, the normal Butterworth filter, it actually doesn't need to use op-amp but several components. You just try to look at, you just try to search for that. Can you do that? And we will see how. Okay.
Okay, thank you for the education.
Because in your library of your software just now, it doesn't have an op-amp, right?
Kind of that, because maybe of the main function of the plugin that I just shown to you is based on how op-amp works, but it's actually a program to create a music, Prof.
Okay. We take a look at Butterworth filter and we will see how. Yeah.
Okay, thank you, Prof.
Yeah, thank you. Okay, thank you for the sharing your question. At least it will benefit your other friends and they will have some idea. Inshallah. Okay, we will proceed with our lecture today. 1 minute, yeah. We have done bandpass filter. High pass filter we have done. Okay, so we are going to look another tool, which is op-amp as differentiator. Okay, if we look at it's not differential. Differential is the difference between two inputs. It's like a subtractor. This is differentiator. The mathematical operation of differentiator, normally we, the other one, after this, we're going to see integrate as an integrator. This is as a differentiator, yeah, the DDT. So another application for op-amp, okay, is as a differentiator circuit, which means it transforms the input waveforms, yeah, versus the output waveform, which means how does it function? A differentiator circuit, okay, is one with where the output voltage, okay, is proportions to the rate of change at the input voltage with versus time. So as a differentiator circuit, okay, the output is proportional to the changes at the input, and some waveforms like the sine wave, square wave, and triangular, okay, will be differentiated, okay, and will be transformed, okay, as different waveform at the output of the differentiator circuit. This is one example. If we have this sine wave, this is what we will receive at the output when it goes through the differentiator process. And it's here as well, okay? And the triangle. Okay, this is the circuit of a differentiator, is when we apply a capacitor at the input section of the inverting input, okay? So what happened, we know that the capacitor will block all the DC signal, so there's no current flow there, okay? And we assume again that here it is virtual ground, and capacitor will only allow AC voltage, okay, to go through, and the frequency will depends on the range, on the change of the input signal. So at low frequency, okay, remember, yeah, XC is equal to 1/2 pi FC. So when at low frequency, when F is low, okay, XC will be high, yeah, and vice versa. So at high frequency, it will be the other way around. And when since the node voltage of the op-amp, okay, is inverting input in this example, okay, so the current of IF, yeah, and IN with assumption of X as virtual ground, so IN is equal to IF, so we will have IF is actually negative because of the input impedance, input terminal, inverting terminal, so we will have V out divided by feedback resistor RF. Okay, the charge of the capacitor will equal to the capacitor times by the voltage, so we will have charge, you know, this when, because this we are talking about time, yeah, differentiate, because differentiator is ddt, okay, dq dt. So the charge will be, okay, the charge of the capacitor will be C, the value of C times by Vn. So the rate of change of the charge will be the we differentiate Q. So it will be dq dt is equal to C. C is normally constant, yeah, d dt Vn. And from there, we can compute what is In, okay? And we will have In, we know In just now earlier is V out over RF. So V out, we have it here, yeah, is C constant, the difference of V in, okay, the differentiate value of V in. So this is the value of V out that we can compute, yeah. So the output voltage is a constant of RF times C that is derived with the input voltage with respect to time, and the minus sign indicate that this is wrong. It is 180 degrees. Sorry. 180 degrees phase shift out of phase because the input signal is connected to the inverting input, okay, of the op-amp. So this is another example of op-amp as differentiator circuit, where we use actually a capacity in series with the resistor and the voltage source, yeah. And again, remember, C and R is constant, okay. What we actually differentiate or we derive is the dV in over dt, okay. And adding a resistor R1 and capacitor CF here is actually to stabilize the circuit at higher frequency and also to reduce the effect of noise. Okay, this is actually practically. So where do actually we utilize op-amp as differentiator? Okay, when we want to design or to operate triangular and rectangular signals, okay, and also when we want to detect high frequency components in input signal. So as a summary, op-amp as differentiator, okay, one, inverting amplifier circuit configuration with reactive components, which is capacitor, okay, then inductor. The differentiator actually will perform the mathematical differential operation with respect to time, yeah, meaning it will, the output voltage will be the rate of change of the input signal. Here, dV in over dt. Here, dV in over dt. R and F is constant. Okay. So, and the differentiating circuits normally used to operate triangular and rectangular signal, F, and if the input signals are sine wave, okay, differentiating circuits will have frequency limitation. Okay. So another configuration of C-in as op-amp as differentiator with capacitor and resistor value. Okay, and here we can see actually one of the application is how the FM signals are converted to the AM signals in our radio as a frequency modulator carrier. Okay, and all filters actually when it comes to R and C, it utilizes this frequency, this equation. Okay, and if we go to look at the scope, this is what we will see. We will see that if it is sine wave, okay, the blue, the input signal is the red one, which is the sine wave, and the output signal will be the blue one, which is sine wave, which is out of phase by 90 degrees. This is because the effect of derivations, yeah, of the sine function, okay, that inverts it to the inverted cosine. Okay, if the input signal, the one in the red, is a triangle wave input, okay, the output that we will receive, yeah, is the blue one. Okay, and how do we get this? You will need to actually derive it using here, and you will receive this plots, the blue one, for that red triangle inputs. Okay, that is actually op-amp as differentiator. Okay, the next one, I think this is the last one for today. Op-amp as an integrator. Okay, as for integrator, yeah, it is something like this. Okay, if the input is 0, the output will stay 0. When the input is increased, the output will increase until the maximum, and once it goes back to 0, the output stabilizes at the last value it is there. So that's why it goes straight here. So as op-amp as integrator, it performs functions with regards to mathematical integration operation. Okay, and it integrates the input voltage with respect to times, meaning at the output voltage at any time is determined by the start of the output voltage. So it starts here, yeah, immediate still 0, so it starts here. And the length of time the input voltage is presented by the value of the input or the output voltage is here. So it will increase. And once it goes 0, it maintains there at the last value it attains. Yeah. Okay. So the basic operation amplifier of an integrator, okay, the capacitor is located at the feedback loop here. Differentiator the other way around. Okay, capacitor is at the input here. Integrator, it is at the feedback loop. Okay, and why we have as such here? Because the input is fed into the inverting input, so it is inverse. When this is high, when this is low, it goes high, and it actually integrates here, and it goes consistent here. The equation for the integration is this one. V out is Y negative because it goes to the inverting input 0 to T until where, and we integrate V in, R and C in constant, we can take it up. Okay, V in dt, yeah, and you know it's like the normal integration, so you know what is actually the low and the high, yeah, and where V out is the output voltage, V in is the input voltage, RC is the value of resistor and capacitor, T is the time after start, yeah, in seconds normally, and C is the constant of integration. Okay, op-amp as integrator, this is with value. Sorry, why is my this one not going up? You cannot see it. Okay, sorry. Okay, op-amp as integrator. Okay, it is actually the opposite of differentiator, the position here. Yeah. So again, it is using the same frequency. F is equal to 1/2 pi RC. Yeah, and if we go to the scope and we try to look what happened. Okay, remember the blue color, the red color is the input. So if we have a square waveform, yeah, the output, yeah, the square wave input will generate a triangle output here. Okay, that's how we will look into in the scope. And if you want to compute it, you try using this equation. And if it is a sine wave, that is the input, yeah, we will actually receive a sine wave also, the blue color, at the output, only it is actually shift at minus 90 degree. It is delayed, okay, because of the integral of the sine function. Okay, so one drawback of integrator, because there is no feedback between output and input, because the feedback here is no longer resistor but capacitor. Yeah. So that is what happened for integrator. So where actually we use integrator, yeah, in ADC, in RAM generators, or if you want wave shape application, yeah, maybe when you go for your integrate for signal that represent water flow, yeah, in industrial instrumentation, okay, and the summary is there for you to actually go through. Okay, we will have one more example here. You can try. This is very simple actually. Okay, how many examples do I have? Okay, I have 2 examples. Okay, you can try this. This is op-amp as a light depending resistor, but it is using the inverting input, okay? So it gives us that R1, R2 at 5K and 50K respectively. And the input voltage is at 1.2 volt. And a high resistor voltmeter measures the output. It asks us to compute what will be the voltmeter reading if the LDR has a resistance of 100K. And then the next one, if the LDR has a resistance of 10K. Okay. And then it says that the light incident, this is actually practical application. This is how actually we compute for practical usage. Yeah. So the light incident on the LDR is provided by a single lamp. With the answers in A, it wants you to actually explain how will be the variation of the voltmeter reading when the lamp moves away from the LDR. Okay, I'm going to share the solution with you. Okay, the first one is actually normal, where we know that RF is 33.33. Okay, how do we compute that? First is when this is 100K, parallel with R2 5K, you parallel it. Okay, you get it as 33.3K, sorry. And you compute AV is RF over R1 because it's into the inverting. And you get 6.6 volt. So when V out is 6.6 volt, you will get, sorry, when V in is, when your voltage gain is 6.66, sorry, you times by 1.2, your V out will be minus 8 volt. The next one, the feedback is 50K parallel with 10K, you will get 8.33. And your V out will be 2 volt. So what happened? So moving the lamp away will decrease the light intensity, of course, kan? So LDL resistor and feedback resistor will increase, gain increase, voltmeter reading increase. That is the correlation. Okay, so if the output becomes more negative, okay, the lamp, the LDR the voltmeter reading will increase, and the LDR resistance and feedback resistance will increase as well. And that will actually move the lamp away. The lamp away decreases the light intensity because the resistor is higher. Okay, that's the first solution. Okay, let's try this one. This is actually microphone. This is the microphone. This is the last example. It wants you to name, first it says, name the type of feedback used with this op-amp. It's either inverting or non-inverting. And how you're going to look into that is you need to look at the source is connected to which terminal of the input, the input of the op-amp. And then it tells that V out is 5.8 volt, okay? And the difference, the potential difference across the resistor R is the voltage, yeah, the voltage drop there is 69 millivolt. Calculate the gain of the amplifier circuit, which means AV. And then calculate the resistance of resistor X here. And then it says state one effect on the amplifier output of reducing this resistor. If you reduce X, what will happen? You try first before I give you the solution. Okay, so let's look at the solution. It is a negative feedback configuration. Why? Because the output is returned to the inverting input. We look here. The output is feedback to the inverting input. So it is inverting amplifier configuration. Yeah. So we know gain is V out over V in. And we know we are given V in as 5.8 volt here. V out is given as 5.8. Okay. And this is actually the 69 microvolt. So we have the gain as 84. Okay. And we are required to compute this. So we know that Rx, okay, is around 1.45 kilo ohm. So if Rx is reduced, the voltage gain will increase and also V out will increase. Yeah, that's what happened if we reduce Rx. Okay, this is some real application of op-amp in ECG as a measuring with bridge, yeah, and also PID controller that I just share with you that you can take a look later. Okay. Okay, I think that's all for today for our op-amp. Thank you. Prof. Any questions before we go off? We still have a few minutes more.
Mungkin kalau ada pertanyaan, silahkan. We will join again on the next Monday. Next
Yes.
Monday ya, Prof?
Yes, Monday, inshallah.
Ya, jadi next week we join on Monday because there is business maybe in Prof Norita, so we shape the schedule on Monday. Jadi jadwalnya kita rubah ke Senin untuk minggu depan.
Yes.
Ya, jadi.
So next week kita akan go for Thai ricer.
Ya. Yeah.
Inshallah.
Jamnya sama Prof ya?
Sama, ya sama.
9 to 11 maybe ya.
Yes, inshallah, same time.
Ya. Silakan kalau ada pertanyaan nih, bagus tadi Mas Iqbal sama siapa tadi Gede ya tadi ya. Pertanyaannya bagus, ada yang pakai simulasi.
Yes, very good.
Ya.
I'm impressed.
Ya, mungkin bisa di-sharing ke teman-temannya itu simulasinya, sharing apa di temannya mungkin bisa belajar nanya gitu. Jangan nunggu Gede sharing tapi temannya bisa bertanya bagaimana menggunakannya. Jadi supaya lebih menguasai lagi di bidang filter, terutama tadi filter kelihatannya ya, buat filter simulation.
Very good.
Ya, silakan, masih ada waktu kira-kira 5 menit sebelum saya akhiri. Oke, Prof, kalau tidak ada mungkin bisa saya akhiri. Thank you for your time, for sharing your knowledge.
Inshallah.
Sorry if there are mistakes maybe, so see you on next Monday.
Inshallah.
Ya, oke. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you.
Thank you to Prof.
Thank you. Take care, everyone. Thank you, Prof. Assalamualaikum.
Waalaikumsalam.